Okay, so this is going to be a quick comparison between the linear motion, which is what we've been working with so far, versus the rotational motion concepts. So that's what we're going to get into today. All right, so for displacement, which is the difference between your final position and your initial position. Don't forget delta means x final minus x initial. All right, this was our linear displacement. Our angular displacement is going to be delta theta. All right, so it's going to be the angle of displacement. All right, so linear motion is straight line motion, and rotational motion is circular motion. Okay, so we're going from straight line motion to circular motion concepts. All right, so for velocity, for linear motion, it was v. All right, for angular velocity, it's going to be this Greek lowercase w. All right. And then for acceleration, for straight line motion was lowercase a. And for angular acceleration is going to be the Greek alpha symbol. All right, so this is the Greek letter A of the Greek alphabet. All right. All right, so the radian is the unit of angular measurement. Okay, so this is going to be essential to understanding these concepts. All right, so the SI unit is going to be the radian now for the rotational motion concepts. All right, so for linear displacement, it was in meters. For linear velocity, it was meters per second. For linear acceleration, it was meters per second squared. So now for the rotational concepts, your angular displacement is going to be in radians. Angular velocity is going to be radians per second. And then angular acceleration is going to be radians per second squared. All right. All right, so on to the radian. So recall the distance around a circle is going to be given by S, and that's going to be 2 pi times the radius. All right. So this is rotational motion. All right, so your distance around a circle. All right, this is going to be denoted by lowercase s. All right, and it's going to be equal to 2 pi r, where r is the radius. All right, so the distance around a circle is represented by the letter S, and S is equal to 2 pi r. All right, where r is the radius. All right, so if you guys remember the XY plane, all right, so when we're talking about radians versus degrees, we have 0 here along the positive x-axis, or 360 degrees, 90 on the positive y, 180 on the negative x, 270 on the negative y axis. All right, so 360 is equal to 2 pi in radians. So 180 is going to be pi. 90 degrees is going to be pi over 2. All right, and then 270 is going to be 3 pi over 2. All right. Okay, so this is going from our angle in degrees to radians. All right, radians For 360 degrees, it's 2 pi. For 90 degrees, it's pi over 2. For 180 degrees, it's pi. And then for 270 degrees, it's 3 pi over 2. All right. So this is just to give you a visual of what we're talking about. All right, so the distance around the circle is lowercase s, and it's equal to 2 pi times the radius of that circle. So if we were to divide the radius by both sides, we would get the circle, the distance around the circle, divided by the radius is equal to 2 pi. All right. And then here, we're just corresponding the radians to the degrees. All right, so the angle theta by the arc along the length S around the circle of radius R, again, is measured in radians, all right? In the counterclockwise direction, right? So going this way from the positive x-axis, all right? So our angle theta is gonna be the distance around the circle divided by the radius of that circle. All right, on to angular position and displacement. All right, so angle theta, which is again measured in radians, is called the angular position. All right, and it's similar to the linear position where we used variable x. So as a point on that rotating disc, as it moves from point A to point B over a period of time, which again, a change in time is delta t, so that's your final time minus your initial time. So your initial angle is going to start at theta I and end at theta f. Okay, so again, your difference here is going to be your final minus your initial. Okay, that's your angular displacement. And again, the SI unit is going to be in radians. So the shorthand for radians is just RAD. All right, on to angular speed. Okay, so angular speed is the ratio of angular displacement, which is going to be our change in theta, so our final angle minus our initial angle, over the change in time. So our final time minus the initial time. So for your angular speed, your SI unit is going to be radians over seconds. For angular acceleration, all right, is denoted by the Greek letter alpha, all right, and it's the ratio of the change in angular speed, all right, change in angular speed over the change in time, right? So your alpha symbol is equal to your angular speed divided by the change in time. So the SI unit for angular acceleration is radians over second squared. All right, linear acceleration was meters over second squared. Right, the SI unit for linear speed was meters per second. Angular speed is radians per second. All right, and the linear displacement was in meters, and the angular displacement is going to be in radians. All right, so this is the relationship between angular and linear quantities. So when you have an object that's going to rotate around a fixed axis, that angular speed and acceleration are going to be related to the tangential speed and tangential acceleration through those relationships. So here you have our speed is equal to the radius times the angular speed, and then you have your acceleration is equal to your radius times your angular acceleration. All right. Let me say that. Add some extra spaces in there. And then we have centripetal acceleration. So this is acceleration or an object that's moving in circular motion on a circular path and has an acceleration directed toward the center of that circular path. So it's around the angle of rotation. The axis of rotation is where that acceleration is pointing towards. All right, so this again is called centripetal acceleration, and it's given by lowercase a. So acceleration, sometimes you'll see a subscript c to stand for centripetal, and it's equal to the velocity squared divided by the radius. All right, and another form of that equation is the radius times the angular speed squared. All right, so on to Newtonian gravitation. All right, so the law of universal gravitation says that if two particles with their separate masses, so let's say mass 1 and mass 2, and they're separated by a certain distance, and we call that distance r, that gravitational force, all right, represented by F, force is represented by F. So again, force is just simple push or pull on an object, and it's going to act along a line that's joining these two separate particles with that given force. So here you have the universal gravitational constant. So this is big G. So big G and small g are different. So small g is gravity, that's the 9.8 meters per second squared. Big G is the universal gravitational constant. So that's going to be 6.673 times 10 to the minus 11 power. All right, so big G and little g are different. Okay, so this is equal to the 6.673 times 10 to the minus 11 power. All right, so big G and small g are different. All right, small g is gravity, big G is the universal gravitational constant. All right, they have different values, they mean different things. All right. And we'll actually get more into that equation definitely in part 2 of physics as well. All right, then we have the gravitational potential energy. So this is where the gravitational potential energy associated with an object at a certain mass and at a certain distance from the center of the earth. All right, so your potential energy, PE, is equal to minus, so negative, and then we have the universal gravitational constant times the mass of your planet. So in our case, we're usually using Earth. Then the mass of the object that's at the distance, at a certain distance, divided by that distance from that planet, which in this case, we're talking about Earth. All right, and then we have Kepler's laws. All right, Kepler derived 3 laws of planetary motion. All right, so the first one states that all planets move in elliptical orbits with the sun at one of the focal points. All right, so elliptical orbit just kind of means like a oval shaped or circular type of pattern around the sun. All right, number 2, a line drawn from the sun to any planet sweeps out equal areas in equal time intervals. And then 3, the square of the orbital period of a planet is proportional to the cube of the average distance from the planet to the sun. So here, T is the period. All right, the period is in seconds. All right, time is in seconds. All right, the period is squared, and it's equal to 4 pi squared divided by the universal gravitational constant times the mass of the large body, whether that's a planet or a sun. All right, S is your distance around that planet divided by the average distance from the planet cubed. All right. So the third law can be applied to any large body and its system of satellites. So satellites just means moons, by replacing the sun's mass with the body's mass. So in particular, it can be used to determine the mass of the central body once the average distance to a satellite and its period, so its rotational period around the sun, is known.